Hi, I'm Ben-Yaakov. This presentation is entitled The Operation of a Single-Stage ACDC Converters for Single-Phase Lines. Now, the conventional way of building a high-power power supply is to include a active power factor correction section at the input, and then usually we are going to have a bulk capacitor, and then a DC-DC converter, which is isolated, usually through a transformer, to stabilize the output and to step down, for example, to 48 volt. Now, the single stage approach is a one unit that includes both the active power factor correction, so you'll have a current which will comply with the current harmonic requirements, and then we have a isolation through a transformer usually, and a voltage which could be, of course, stepped down. Now, in this presentation, I'm going to explain how a system like this is built, a single-stage AC to DC, and the principles behind it. I'm going also to show some examples from published papers. So what is the concept that you'll find in any one of these single-stage AC to DC topologies? You're going to see these three units. At the input, there's going to be a chopper. That is, to take the AC voltage and to chop it into a high-frequency voltage, bipolar. And the reason is that you like to have a high-frequency transformer rather than a lower-frequency transformer, of course, and that you don't want another converter here. So this is already creating the high frequency. So here we have a modulated signal, AM modulation, you might say. The envelope is the input, and it is chopped bidirectional by this chopper here. Then we have this current control unit, and the purpose of which is to generate a current which is proportional to the voltage at any given point, any given instant. That is, if we are at a voltage, say, of this magnitude, which is corresponding, of course, say, to this magnitude, then we want a current which on the average will be proportional to the voltage. So at each voltage here, we have a current proportional to it. So we are creating on the average a sinusoidal current, which will be, of course, in phase with the input, which is the requirement of the active power factor correction. I'm not talking with a high frequency ripple that has to be obviously filtered out. So the function here is to generate these currents cycle by cycle that are proportional to the input voltage. And then we have this isolation and a rectifier that could be either a passive, say, diode rectifier, or preferably, and it's important in some realization, to have it actually active rectifier that you can operate it sort of like a dual active bridge, okay? So in some cases, you might say that the system is something like a dual active bridge, because usually you'll have here a bridge, and then there is another bridge here. So it is sort of a dual active bridge, but of course the functionality is different. So let's go over each one of these units. So the chopper is a full bridge or a half bridge that can receive a rectified voltage. So it'll be like a positive voltage. So in this case, you can use a unidirectional switches like a regular MOSFET, or you can operate it without a rectifier, but then you need a bidirectional switches. I'll show an example in a minute, which can accommodate a positive and negative voltage, okay? And this, of course, can also be a full bridge or a half bridge. The result of this chopper should be something of this nature, that is a voltage which is chopped. So we have a carrier, which is this switching frequency, and then the input now is the sort of the modulation of this carrier. Now, if it is a bidirectional switch, then you can realize it by a two-tran MOSFET transistor unidirectional back-to-back, very well-known approach. Or recently we have this bidirectional switch, an integrated element announced by a number of manufacturers. So this is one unit, It's basically realizing this configuration, but it's one chip here. It has two inputs, and it is bidirectional, and some of them are of the gallium nitride technology, so they can be operated at very high frequency. So this is how this chopper can be realized. Now then we have the rectifier that of course could be a simple diode rectifier, but preferably, and as we'll see, required for the operation, we'd like to have, I'd call it an active rectifier, something like a synchronous rectifier, except that it can also work in modes like having a short at the output. And this is by operating these two transistors, you can have a short, and it turns out that it is needed in some of the single stage topology. And now we come to the heart of this unit, and that is the current control. Now the function of the current control is to generate a current which is proportional to the input voltage. So at each switching cycle, we need to have a current which on the average is proportional to the voltage at this point. And this, of course, realizes the active power factor correction. Obviously, the magnitude of the current is a function of the output, and then it could be in open loop if you know how to program the operation of this current control within the line cycle, or preferably, I think, with the feedback, so that for each given voltage, you generate the correct average current. So just to get an idea of how such a current control can operate, let's consider the case that we have a transformer and an inductor in series. Now, this could be a leakage of the transformer, and this would be for high frequency and maybe a moderate power level. High power level and high frequency, you like to have a separate inductor. So let's assume that at one point we have this circuit connected like this. That is, the diode is clamping the transformer to the output. So we have the output reflected to the input. And then if we have a voltage which is higher than the reflected voltage, we'll start to build up a current, a linear ramp here, according to V in over the inductance. And then at the end of the pulse, the current will go down. So on the average, we're going to have an average current, which is the peak divided by 2, which is proportional to the input. Now, this will work, of course, if the voltage is higher than the reflected output. If not, what can be done when the input voltage is low, you can have a short here, and this is by the active rectifier, having the two transistors at the bottom contacting, so there is a short. And then you have this inductor connected to the input directly, so the current will go up depending on the input voltage divided by the inductance, and then you can release this short and connect the transformer to the output. And by this, the energy will be transferred to the output. At this point, of course, the slope will be lower because the voltage difference is smaller. So by having this active rectifier, you can do a lot of things, and to accommodate the situation in which the input is of low voltage. That is, we have instances of low voltage and high voltage. And here is an example of such an approach. In this paper, there's no experimental result, but I brought it because it's simple to understand, I think. And what we have here is indeed a case of no rectifier. So the input, except for a small high-frequency filter here, the input is connected to this half bridge, which is built around this back-to-back 2 MOSFET, so it's a bidirectional. So this bridge can operate with a positive voltage or a negative voltage. It will generate this square wave, this modulated signal. And here we have the inductor, transformer. And here is this active rectifier that we can operate it in various ways in order to get the average current to be proportional to the input voltage. And here are some two modes of operation which are used for different region of the line cycles. And what we see here is this is the input, chopped input, or here it is, at a given instant, of course. And then we have the output voltage. Here, you see here we have a 0 here, the case, as I've said, to boost up the ramp here. So we can generate a current with an average proportional to the input voltage. Now, as you can see, there is here an instant in which the output is actually connected in the reverse direction. By this, the ramp is made very fast so that the commutation between the negative and positive part is shortened, okay? And here is another mode of operation, and the difference is that you see the phase shift between the input and the output. I'm not going into all the details of the way the switches are being operated, just to give you an impression of what it is all about. Now, in this paper by Professor Kohler and co-workers, the approach is similar to what we've just seen, except that we have here a full bridge and that these are not bidirectional transistors. It could be a MOSFET. And here we have a rectifier, so we have a rectified voltage. So this bridge will always see a positive voltage, so therefore we can use regular MOSFET, okay? But then we have this inductor transformer, and then we have this active rectifier at the output. Now this paper has experimental results. And here is one example. We see here the input voltage, we see the input current, and as you can see, we have a very good waveform of the current. Now the gist of this paper is how to do the optimal modulation to get a fine shape of the input current. Another approach is to use an LLC. Okay, this is this paper here. And here is the idea. In this case, again, we have a rectifier. This is just a synchronous rectifier. So the transistors here are unidirectional, like regular MOSFET, because they see always positive voltage. And this is now the chopper, which is then feeding the signal into the LLC. This is an LLC converter. This is the series inductor, parallel inductor, and the resonant capacitor, and the transformer. And then we have this again, active rectifier here, which is used again to boost some of the voltage. Problem here, of course, is that you need a very high gain when the input voltage is low. Okay, at this point, you need very high gain, and the native LLC will not be able to operate in such a high gain. So in this region, something has to be done, and what is being done, in fact, is to short out the output and then to work in the mode that we talked about it with this inductor in between the input and output and getting the ramp. So here is some results, experimental results that they have. Again, we have the input voltage, we have the input current. You see that there is a problem here, and this is because you need a very high gain from the LLC that it cannot produce. So the mode of operation here is different, and this is actually reverting to the idea of this inductor which you charge and discharge. And here are some efficiency results, and this is for 2 points. You see for the 500 watt, 400 volt is 0.97, and for the 250 volt, 330 watt, 0.9N, which is pretty nice. An important point that needs to be made is that although we have a 1 unit, and obviously we don't have a bulk capacitor in between because there's no in between. We need this interconnection between the chopper and this current control. Still, we would need a bulk capacitor, which usually will be put at the output. And the reason is that the input voltage is sinusoidal, the current is sinusoidal. This is the objective of the whole thing. And therefore, the power coming in is sine square. It's pulsating. We want a continuous power. So during this time, we need to store energy that will be released during this time so as to accommodate the requirement of the output. So no matter what you do need a bulk capacitor. Now, if the bulk capacitor is the output and the output is a low voltage, the capacitance will have to be very large because it is a function of the voltage and the allowed ripple. In fact, it's proportional to the output times the allowed ripple. So if the voltage is low and the ripple is moderate, then you need a large capacitor. So let me summarize that to realize a single stage unit, you need these three components. You need the chopper, you need the current control one way or the other, and then you need a rectifier, which usually will be an active rectifier, so you can operate it in different modes. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.